Now, as you can understand, let me just tell you briefly that tomorrow is your class test. So tomorrow sharp at 9, please be present. I'll be uploading the questions, and by 9:45 you have to finish the answers, and then within 9:45 from 9:45 to within 10. Okay, this 15 minutes I have given you the time to save it in a PDF, it's single PDF, scan it and save it a single PDF file, your answer script, and then send it to me via email ID, via my mail. Okay, via the mail, I will be providing the email ID. So only single file, and please keep the name of the file as it is directed on the question paper. Okay, so please be there, and if anybody is going to miss that time, okay, the time limit, so his answer copy will not be evaluated. And be careful that some of you may write exactly the same lines or the same words as the notes, and if I find that if there is any similarity between the two notes, or if there is any similarity between the class notes and your writing, it will be cancelled. You have to read and you have to write in your own words. It is not just that you will be copying and writing the answers and sending it to me. Okay. So let's start for today's class. This is if you are going to see the yes.
So कौन-कौन से chapter आएंगे sir?
I have already informed in the WhatsApp a long time ago. These are the first 3 chapters, chapter 1, chapter 2 and chapter 3. Please follow the instruction of whatever I have given in the WhatsApp or in the class MS team. Okay. The first 3 chapters are for the examination. Okay. So for the fluid flow, if you are going to discuss about the fluid flow, this part of the discussion is going to give you the idea. First is about the gas diffusion through the cold matrix. Why cold matrix? Because gases are absorbed into the pore system or the pore network. Okay. So then when the diffusion is going to take place, what is happening? From the pore, the gases into the fracture system. That is once they have reached the fracture system, they have also transformed into the free state from the adsorbed state. Okay, so that's why whenever the diffusion is going to take place, it is only after the diffusion the gas flow will occur or will start based on the Darcy flow. Okay, so that's why after this gas diffusion, you can see that the gas flow through the natural fracture systems. Okay, and then it will also discuss about the measuring the fracture system properties from the cores. From the core sample you are going to collect from the core barrel, how we are going to measure the fracture systems. Some of you may have the idea from your rock mechanics class or your geology classes that how we are going to estimate the fractures. Okay, the deep direction of the fractures or the beds, so that you can understand the different properties of the different rock components. Okay, in a core sample. And then obviously the last item to discuss is the fluid properties. Fluid properties means gases and the water, combining these two phases, they are going to prepare the fluid. So whenever the individual gases are there, the individual gas or the individual water properties or the reservoir properties, okay, reservoir properties is already there. Okay, but these reservoir properties, there will be some changes into the reservoir properties when you are going to extract the water. Okay, and obviously the moment you are going to extract the water, its saturation, its permeability, the relative permeability between the gas and the water, this is also going to change. So there is a dynamic state. That means dynamic means varying with time. So there are some dynamic property changes which is going to affect the gas transport system. Okay, so that's why it is very much important to see these parameters. Okay, now let us start with the diffusion. Okay, so in the diffusion, the gas diffusion, you understand that from your discussion of the chemistry or in the 12th class chemistry, you know that the diffusion means that one phase is going into the another phase, it is diffusing, okay, and it is depending on the two systems or the different systems, okay. And here the concept of the total pressure and the partial pressure will come. If there is only one phase, if there is only one component, then everything is only pure gas or the pure component, okay, only one component. But the moment when there is a mixture, okay, when there is a one phase is going to diffuse within this other phase, so obviously there are two mixture, there are the mixture of the gases of two components. So in that case, the mixture properties or the mixture properties will be going to depend on the fraction of the each individual component present into that mixture. That means suppose you are going to do the adsorption of a gas mixture of suppose 30% of methane and 70% of carbon dioxide, then the total gas absorption will be going to depend on these two components, 30% of methane and the 70% of carbon dioxide. If you are going to change this absorption fraction, this gas fraction, but you are going to remain the constant, you are going to keep constant the experimental temperature and the total pressure. Suppose you are going to consider the temperature at 30 degree at some temperature, and you are going to conduct the test from 0 to 6 megapascal, okay. So even if your temperature and pressure are the same, but if your gas fraction are going to be different, your total gas absorption capacity is also going to be different, okay. That is the concept you have studied, that depending on the adsorbed gas fraction, your gas storage capacity is also going to change, okay. So in the diffusion, it is observed that in the porous media with the larger pore size distribution means, you know that there are three different type of pores. The micropore, okay, less than 2 nanometer, 2 to 50 nanometer is the mesopore, and the macropore is more than 50 nanometer of particle diameter, okay, of the diameter. So the pore network means combination of all these three: mesopore, micropore, and macropore. So it is observed that in any type of porous media, okay, there is a mass transfer which is going to be governed by the pressure gradient. Whereas it is observed that in the coal, specifically in the coal, this mass transfer is governed by the concentration gradient. Concentration gradient means what amount of the mass or volume is going to be transferred to the one side from the another side, from one side to another side per second, okay. So this is depending on the concentration gradient, based on the concentration in mass or volume of that gas or the adsorbate here, okay. So whenever you are going to consider this coal, there may be a chance that some part of the gases are diffused by depending on the pressure gradient, but it is neglected because the fraction is very less, okay. So for cold diffusion, you all need to understand that this cold diffusion is going to be take place by the depending on this concentration gradient only. If there is any such pressure gradient depending phenomena, that is neglected, on that is very small in compared to this concentration gradient, and that's why it is neglected, okay. So let us see about the diffusion characteristics. Now the diffusion, as you know, diffusion is governed by the Fick's law, okay, after the name of the scientist. The Fick's law, what is the Fick's law? Fick's law assumes that the mass flow rate, the rate of mass flow from one point to another point, okay, maybe the Q, okay. Q is the mass flow rate in meter cube per second, or if it is the mass flow rate, it is the kg per second. If it is a volume flow rate, it is the meter cube per second, okay. So mass flow rate across the surface is proportional to the concentration gradient across the surface. Concentration gradient means how much element or how much composition of the gases are concentrated from both the sides, okay. Suppose depending on the surface, okay. Just like the pressure gradient dp dx, there is a concentration gradient of dc dx maybe, okay. So with unit length, how much is the concentration, okay, how much material is accumulated at that surface. So based on the differences from one point to another point, the concentration, the gas diffusion will take place. Okay. So what are the other parameter? The gas diffusion is proportional, the mass flow rate across the surface is proportional to the concentration gradient across the surface, the area of the surface, and the diffusion coefficient of the material through which the diffusion occurs. Diffusion coefficient is nothing but the measurement of the rate of diffusion with the area. Okay, that is called the diffusive. Sometimes it is also called the diffusivity or the diffusion coefficient. Okay. Now, depending on this mass transfer, okay, this mass transfer is going to be governed. There are three different individual processes. There are three different individual processes. Okay, I am going to discuss. Now, if you are going to see the equation about the Fick's law, okay, the Fick's law equation, the more corrected equation is given by the 419, equation 419, okay. This is the mass flow rate equation as per the Fick's law. Okay, let us try to understand the equation, though you need not to remember. Okay, but this is very important equation. Okay, as you have seen that for the gas storage also there is a fundamental equation which is called the Larmor equation. So for mass flow rate for diffusion also this is the fundamental equation. Okay, so first Q GM is the gas production rate from the coal matrix. That's why the M. Okay, gas from the matrix. It is the capital M, so 1000 standard cubic feet per day. Oh, okay. So being an engineer, you should not forget to provide the unit. If you are not giving the unit, there is no basis, okay, no mean of understanding about what you are going to refer. Vc is the volume of the coal matrix, okay. Rho c is the density, okay. And then sigma is a particular factor. Sigma is called the shape factor, coal matrix shape factor in reciprocal of the centimeter square. What is the shape factor? I am coming later. Then D, capital D is the diffusion coefficient, which is measured in centimeter square per second. Okay, how much gas is going to diffuse with this area per second. Okay, the GC bar is the average gas content which is measured from the disruption canister testing. Okay, that means if you know the disruption canister testing of a sample, you can approximately assume or approximately measure or estimate what is the gas content of that scene. Whereas a GS is the storage capacity of the coal matrix evaluated at the average pressure of the natural fracture system. Average pressure means if you are going to measure the natural fracture system pressure, the pore pressure, so at that pore pressure, what is the storage capacity of the coal matrix that you need to calculate. Generally, this GS, this gas storage capacity is given by the isotherm graph because isotherm graph is related at a particular pressure. Okay, so GS is estimated from the isotherm graph and GC from the disruption canister testing, and with this you are going to calculate the D. Okay, now the shape factor is going to give you the idea about the sizes of the coal matrix factor. Coal matrix, okay. The shape factor is given by the Warren and Root, and hence it is depicted as the Warren and Root shape factor. Okay, and these are the values of the shape factor which you have to consider when you are going to consider the equation. Okay, so you can see that the depending on whether it is a cubical shape, whether it is a spherical shape, or whether it is a cylindrical shape or slab shape, the shape factor is going to be incorporated. Okay, and you can see that all the radius or length or the equivalent radius or the slab length are going to be put in the denominator. Okay, and that's why the centimeter square is an inverse. Okay, so it is a centimeter to the power -2. Okay, please be careful that. And then using this shape factor, you are going to calculate the diffusion coefficient. Okay, so this is the fundamental equation for calculating the diffusion coefficient. There are Fixed law is there is a partial differential equation. It is not required at this moment right now. Okay. Now coming back to the diffusion process. Okay. As I mentioned earlier, that there are three individual diffusion processes, and one of them can be taken place simultaneously with the other one. Okay. What are these three cases? These are the bulk diffusion, Knudsen diffusion, and the surface diffusion. These are the three important diffusion parameter. Okay, three important diffusion properties. Okay, so whenever you are going to see this diffusion, you have to think about the three types of diffusion. What are these three types for? Stands for? Let us see. The bulk diffusion is dominated by the intermolecular interactions and includes diffusion of one molecular species through a mixture of the different molecular species. Okay. So bulk diffusion or the main diffusion, if you say so, the bulk diffusion is dominated by the intermolecular interaction. That means the different molecules of gases or the different molecules of the coal are going to interact with one another, and so the gases are transferred. The mass transfer is taking place from one molecular species to the other molecular species. Okay, in a mixture of the different molecular species. Okay. So this is the case of the bulk diffusion. This is the first type. Second is the Knudsen diffusion. Knudsen diffusion, what is this? It is dominated by the molecule and the pore wall interactions. So first case in the bulk diffusion, we are going to discuss about the bulk diffusion, which is related to the intermolecular. Okay. Second is the Knudsen. That means one is the diffusion is from the molecule to the pore wall boundary. Okay. Why this pore wall is coming? Because after only crossing this pore wall, the gases will be going to be located at the natural fracture system. Okay. So first is within the pore or the intermolecular diffusion. Second concept is that from the molecular diffusion to the pore wall diffusion. So now it is going from the outside boundary of this pore. Okay. Okay. So pore to the pore wall, molecule to the pore wall boundary, and the third one is for the surface diffusion. What is the surface diffusion stands for? The surface diffusion is mass transfer occurs by movement through the soft state fluid without the mass transfer into the free gas state. The surface diffusion means, suppose in the second case, the gas has reached the pore wall boundary. Okay, with the depending on the concentration, the gas has been transferred from the pore to the wall boundary, and then they are going to be in the natural fracture system. They have crossed the pore wall boundary. In the third case, the surface diffusion, they are going to say it is going to be mean that without any mass transfer. Okay, the mass transfer occurs by the movement. By the movement means by the movement through the soft state fluid. That means in the gas, you know that the gas molecules are in the soft state. It is coming as a free state. So what is happening? There is no mass transfer, but the fluid within the pore is going to be changed because the gases are changed from the particles are changed from the soft state to the free state, and now they are going to reach in the natural fracture system as a free state. Okay, and you already know that the gases which is stored into the pore network that are in the soft state, but some amount of the small gases are stored into the free natural fracture systems. It is in the free state. So in the last stage of the diffusion, which is the surface diffusion, the pores or the gas particles are reaching to the natural fracture systems, and by the surface diffusion process, where there is no mass transfer, but the mass transfer is occurred by the fluid transfer only from the soft state to the free state. Okay. So try to understand these three phases. Okay, these are the three different phases of the diffusion, and collectively 1, 2, or all the three processes can be taken simultaneously, can occur simultaneously. Okay. So next is that when they are going to this transfer, the mass transfer is going to take place. Okay. So what is happening actually? What is happening? You know that the primary porosity is the pore network. Okay, and the secondary porosity is the fracture network. So diffusion is the process bridging the two pore size, the two pore network. How? Because it is only after the desorption diffusion can take place, and desorption is the related to the desorption is related to the pore network, the matrix pore network, whereas the cold transport is related to the natural fracture system. Okay, so the diffusion is going to take is bridging these two processes, and it is occurring inside the matrix and near the matrix, the pore to the fracture wall boundary, or from the from the adsorbed state of the pore wall to the free state into the fracture system. Okay, so these are the three processes that are going to occur, and based on the concentration difference. Okay, what is the concentration difference? The concentration difference that controls the diffusion is the difference between the average gas concentration within a matrix element and the gas concentration at the primary secondary porosity interface. Okay, what is the meaning of this? The first concentration is within the pore. Okay, obviously because the gas is situated at the pore, so the matrix, the concentration of the matrix is obviously going to be important. Okay, so at this case, the first case, the matrix concentration is there, and the second case is when the gases is going to be transported to the fracture system or from the pore to the fracture wall boundary. So then that concentration, so there is 2 points. First is within the matrix and second is outside of the matrix. So the concentration difference of this 2 point is going to allow the diffusion of this gas. Okay. Now, this soft gas molecule at the interface are assumed to be in the equilibrium with the free gas molecules within the secondary porosity. Okay, the soft gas molecules at the interface means the pore wall boundary. Okay, that is the interface because it is in the middle point. Okay, so whenever the pore wall boundary diffusion is going to take place, the gases are moving from the cold matrix and coming to the pore wall, but it is assumed that they are also in equilibrium with the free gas molecules. Otherwise, what will happen? Otherwise, at this point, they are going to transport. They can be moving toward the surface by the pressure gradient. No. Okay. So whenever the soft gas, the pore wall boundary, the soft gas molecules are coming from the matrix to the wall boundary or the fracture wall boundary, they are also resting there is in equilibrium with the free gas molecule, and then the surface diffusion is changing them from the free gas state to the from the soft gas state to the free gas state, and then only the transport can occur. If they are not reached in the free gas state, then obviously the desorption will continue. Once the desorption will continue of a particular particle or a gas molecule, how the transport can be possible? Because the gases has not completed the desorption. Okay, so that's why you have to, the particle has to complete the desorption and it has to reach from the soft state to the free state, and then only the gas transport can occur. Okay. So these are the some of the concept of the diffusion. Okay. Now, as I have discussed about the diffusion equation, this is the diffusion equation from the based on the concentration. Okay, where C is the concentration given in the gram per cc, and then with this they have given the gas content. The GC is the gas content of the scene. Rho C is the ash-free, moist ash-free cold density. That means DAV basis, moist ash-free, ash-free. Okay, so it is moist cold or wet cold, not the dry sample. Okay, and then the gravity of the soft gas related to the air. It is dimensional. Gravity means whether this soft gas which is coming out, okay, it is lighter than air or which is the denser than air. Based on that, it will stay in the upside or it will go to the downside. So that gravity factor is going to be taken place. That's why it is the dimensionless, because the gravity is expressed with the ratio of the densities with in terms of air. Okay, so this equation has been also given for the concentration, whereas we are going to follow this next equation as a main equation of this diffusion. Okay, now there is a concept that if you are going to we have assumed that the CBM reservoir is a dual porosity and single permeability. Why dual porosity? Because primary porosity with the pore network and the secondary porosity with the natural fracture systems where the very few amount of the gases are stored. The primary porosity is having more or less 95% of the gas, and the single permeability. Why? Because across the bedding plane or through the bedding plane there is no permeability, there is no fluid transport. The fluid transport is only occurred through the natural fracture systems of the facelets, butterlets. Okay, so the simplest porosity model means this concept is for the dual porosity models, but the simplest porosity model, they are going to predict that the cold bed methane reservoir behavior ignores diffusion by assuming that the gas concentration within this primary porosity is equal to the sorption isotherm storage capacity equivalent at the secondary system pressure. So if you are going to assume the simplest model with the single porosity model, so then it is going to be assumed that whatever the diffusion is taking place, this diffusion is ignored. Why? Because the gas concentration within these pores, whatever the gas concentration or the gas saturation, if I say so, the gas concentration within these pores which are staying in this adsorbed state, okay, the gases, it is equal to the sorption isotherm storage capacity evaluated at the secondary system pore pressure. That means which is given by the isotherm. But why they have ignored? If they are going to ignore this, they are going to ignore the diffusion process, because they have taken that whatever the concentration, that is the same as the isotherm graph pressure gradient factor. But that is not the case always, because a pressure gradient factor cannot be same with the concentration gradient factor. That's why the dual porosity models need to be considered. Okay, and so in the dual porosity models, they have considered that the effects of the flow between the matrix and the fracture is to be taken care of. So that's why the diffusion is a separate process. Okay, and in this case, the dual porosity model, they have considered that okay, the desorption will take place and then there will be diffusion and then it will move with the Darcy flow. Okay, and so by this concept, the Warren and Root, the scientists, they have given the following equation of 419, okay, which we have discussed earlier. Okay, now in this case, as I have mentioned earlier, that the shape factor is going to depend on the what is the shape you are going to take care of, whether it is a rectangular matrix, whether it is a spherical matrix, whether it is a cylindrical matrix or so. So based on this, there will be different geometry and there will be different shape factor. Why shape factor is going to be important? Because as you can understand that the shape factor, depending on the shape of the surfaces, okay, it will be giving the contact with the gases. Suppose if there is a rectangular slab or the cubical slab, you can get only the 6 surfaces, okay, the outer surfaces. Whereas if it is a spherical surface, it is totally a single surface, okay. Now, as your outer surface is going to increase, the chances of the adsorption, diffusion, or the adsorption, resorption, or the diffusion is always going to increase. Why? Because whenever you are going to increase the surface area, the surface contact, because the adsorption, and there is another term which is called the absorption, okay. Do you understand the difference between this term, absorption and the adsorption? Anyone?
Yes, sir.
Okay. So whenever these two terms, you know that whenever you are going to increase the contact area or the surface area, whenever the gases will come, the gases, the more surface area, the gases have the most chances to go through the surface or form a layer, form different layers on the surface. So that's why the adsorption and the absorption both depend on the type of the shape or on the exposure of the surface area. So depending on the shape factor, obviously you are going to increase or reduce the surface area and surface area contact with the gas, and so obviously the gas adsorption and the diffusion is going to be changed. Okay. Now, sometimes there are some direct method. Okay, direct method means to calculate from the adsorption. Okay, calculate from the desorption concept test, and you are going to calculate by this equation. Okay, the direct method they are going to use the diffusivity. What is diffusivity? It is d by r square. That means how much rate of diffusion going to occur depending on the square of the length from one point to the other point. Okay, this is called the diffusivity. Okay, now the diffusivity they are going to if you are going to measure this, okay, you can see here the ratio, the definition of the diffusivity is given. Diffusivity is the ratio of the diffusion coefficient to the square of the average diffusion distance. Okay, so this is the definition of the diffusivity. Okay. So diffusivity or the diffusion coefficient both are going to give you the idea about the diffusion of this gas to the coal. Okay. So whenever you are going to measure this, you are going to calculate this, and with after dividing this capital D in equation 419 with the square of the distance, maybe if it is the spherical then r square, if it is the length or the slab then the L square. Okay. So from there you will be able to get the diffusion coefficient. Okay, measure the diffusion coefficient. However, in the indirect method, okay, which is a much more commonly method, which is called the sorption time. Okay, King et al. After the scientist of named King, I have already introduced about the sorption time. The sorption time is going to be defined as the time which is required to dissolve the 63.2% of the initial gas volume. Okay, so it can be also expressed by the equation number 420. Okay, as you can see, delta Gc and then Gci. That means the fraction of the gas content or the fraction of the gases that has been dissolved with respect to the initial gas content, GCI, initial gas content, okay, and which is going to be measured as 1 minus exponential to the power sigma capital D and T, where delta Gc is the cumulative dissolved gas content, okay, T is the time in seconds, sigma is again the shape factor, Kohlmeister shape factor, and D is the diffusion coefficient given by centimeter square per second. The characteristics time, which is again known as the sorption time, can be defined using this equation as tau is equal to 1 by sigma d. So you can see that if you substitute this, okay, substitute this, then you will be able to provide, you will be able to calculate the sorption time, and based on sorption time, because you already know that the rate of adsorption or the rate of desorption is going to be related, inherently going to be related with the diffusion. Sometimes we are going to estimate the diffusion with the rate of adsorption. That means I'll show you later that if you are having the isotherm graph with pressure, and if you can measure the time data analysis with the pressure variation, with each second you are going to have the pressure data. From that data you will be able to calculate the diffusion coefficient, okay, because you will be going to plot it, you will be going to plot the diffusion coefficient with square root of time, and from this some formula is there with the square root of time. You are going to plot the graph, and you are going to get, depending on the slope of the graph, you are going to get the diffusion coefficient. This data and the all, okay, so it will be also clear for you. But this, for this time being, you just consider that at this point of time the diffusion can be also estimated by the sorption time or the characteristics times, which is going to be defined as the time required to dissolve the 63.2% of the initial gas volume. So suppose if it is not your characteristic time, okay, then you can take for your if you know the initial gas content, and depending on the gas content you are going to, depending on the gas storage capacity at each point, at each fraction of the resorption or the gas is coming out resorption, you will be able to calculate what is the time required, and so you will be able to calculate again what is the diffusion, because as you can understand that the rate of isotherm, the isotherm graph, the shape, you remember what is the shape, okay, in the initial pressure it is very much high, and then it is as the pressure increases it is going to become flatter. So if you are going to do the adsorption or the desorption, obviously the rate of adsorption desorption is going to change, and simultaneously the diffusion rate is also going to change. Okay, you will see that at some initial stages very high amount of diffusion will take place, whereas where there are in the final cases or the higher pressure the diffusion is very less. Why? Because most of the cases the gases are already going to be adsorbed, and the pore spaces are already filled up. Okay, so these are the two different methods. There is the indirect method and there is a direct method by which you can calculate the diffusion. Okay. So any questions regarding this? You have understood whatever is discussed so far? Okay. So the next concept is the gas flow through the natural fracture systems. Okay. Now, before we are going to start this gas flow natural fracture systems, there are certain factors you need to see. Okay. You know that the gas flow is totally depending on this pressure gradient. Okay. And at this point of the natural fracture systems, you know that some amount of the gases can be stored in the free state, or after the diffusion, the gases has been transformed into the free state from the adsorb state. Okay, so what is going to happen that after the diffusion, let us, if you are going to consider that it is a mutual process, it is a mutually exclusive process, that one particle, that some particle, it is dissolved, it is diffused, and the gases are now into the free state, and so the gas particles are ready under the Darcy flow. It is going to be transported into the surface. Okay, but remember it is not a mutually exclusive process. These three processes of the desorption, diffusion, and the Darcy flow can be considered simultaneously at some point, and obviously as you are going to take out the water, some of the reservoir properties are going to change, and some of the gas properties or the fluid properties are also going to change, and they are going to affect the gas production. Okay. Now, in a summary, we have to discuss this type of parameter. What are the parameters? These are the important parameters. Okay, that you need to learn. Okay, let us see what are the parameters. First is the average pressure. Now, today I'll be just giving you the idea of this parameter. In the next class, after tomorrow, we'll be going to take one by one parameter, and we're going to see what are the each parameter is going to discuss. Okay. So the average pressure means the fracture system pressure. In the pore, there is a separate pore pressure. Okay, the gases are adsorbed, and so the pore pressure may be much higher. Whereas in the natural fracture systems, the gases are in the free state. So the gases pore pressure here is much more less than the pore system network, because pore is also very much confined, and in the fracture system it is very much free state, so the pressure is very much less. So you need to consider the pressure first, because transport is obviously the pressure dependent process. So first you have to consider that at which pressure the flow will take place. So, and it is not the pore pressure, but it is about the fracture system pressure, so that pressure is required. Next is the classification of the natural fractures, the different types of the natural fractures. Okay, the different types means then first face slits, butt slits, etc. Then is the reservoir geometry. the coal matrix geometry and the orientation of the fractures, the spacing, everything, okay, the frequency, those things are required. Effective stress conditions, because based on the effective stress, the pressure, the pore pressure is going to change. You know this effective stress condition, I think, okay. This effective stress will come whenever there is a pore pressure is there, or whenever there is a water saturated into the reservoir, okay. Then comes the fracture system permeability, the porosity, and the pore volume compressibility. Permeability is to permeate the flow of water. Porosity is going to depend on the porosity of the fracture system, not the coal matrix. That means the porosity means the spacing of the apertures, or the how much, whether it is filled with the other rock material or it is the total open fracture systems. Okay, that's that amount of the porosity. And third one is the pore volume compressibility. How much with the pressure, the pore volume in the fracture system, okay, how much it is going to compress or whether it is going to be extended. Okay, if you are going to consider that it is an elastic media, so how much is the extension on the compression based on the pressure. Next point are the saturation. Okay, saturation or the normalized saturation. Saturation means the saturation is whether it is water or oil saturated, and the normal saturation means with respect to the individual component you are going to put it in the normalized saturation. Suppose there are two mixture, so you are going to take, then you are going to tell that the water saturation is only 30% and the 70% is the oil saturation. But then in the normalized situation, you can tell that okay, with the ratio of this 30 to 70, how much is the water saturation is available, or how much is the oil saturation is happening. Okay, that's why it is called the normalized saturation. That means the area which is supposed to have the water, how much of it is going to filled by the water. Okay. And so for the oil. Capillary pressure, you all know about this capillary pressure, okay. Relative permeability, as I mentioned earlier, that whenever there are two or three different phases or more number of phases, there will be no concept of the absolute permeability, there will be always the effective or the relative permeability. Effective permeability is somewhat different, okay. Relative permeability means in relation to the other media, okay. Suppose there is a gas and the water, so relative permeability of the gas with respect to the water, or relative permeability of the water with respect to the gas. And last one is the estimating the fracture system porosity and the permeability. The fracture system porosity of a total seam, how your fractures are oriented, how your fractures aperture are there, whether they are constant, the apertures are constant from one point to second point, another point, or it is going to vary from one end to another end, it is going to be filled with some rock type from one end to another end, or it is just having some irregular asperities. You know what is it called, asperities? Anyone? You understand the term asperities? Hello? Do you understand the term asperities?
No, sir.
Okay, if you are, suppose there is a sample and the sample surface is broken, okay, the core sample, it is broken by its diameter. So what you will get, if it is not cut, the broken surface will not be a straight line, there will be always a irregular broken surface. That irregular broken surface is called that asperities, okay. That irregular broken surface is the asperities, and then once it is broken, if you are going to put the two parts side by side, you will see that it is never going to fit in intact, just in the earlier case before breaking. Why? Because the asperities, now it will increase the volume. Whenever there is a breakage of the rock sample, its volume is going to increase because the asperities is going to affect the surface, and they are not going to put this into the actual surface. Okay, so these are some of the parameters which we need to discuss, and we'll start the discussion from the next classes. Okay. Now let me tell you that I can see some of the students are putting this on hold, and I don't know what they are doing by putting the on hold button. Okay. In the class, if I see that someone is putting on hold, and I'll be canceling this attendance, okay, his or her attendance. So be careful, and let me remind you that it is not an easy concept, just like other your mining core subjects. So it is very much important for you to pay the attention in the class. And I know that you all will be going to start the preparation for the examination just before 1 or 2 days ago. And if you think that at that point of time, if you are going to ask me about or make me understand about certain thing, I may not be available at that point of time. Okay. So be careful, and be a little bit. You are much more senior now, so I hope that you don't put any activities which will going to be creating a negative effect for negative image on you. Okay. So I can see that who are present and who are idle, who are on hold and who are not present. So please don't do this. This is totally visible. Okay. And by the time if I'm going to take any viva after the examination, or if I'm not going to take any examination and I'm going to consider the viva, you may be in trouble again. Okay. So please try to understand, and please try to attentive in the class. Okay. So any questions? Otherwise, I'm going to leave you for today.